Thank you for joining us. My name is Amy Clements, and I will be your host for today's webinar. Today's topic is Digital Engineering Basics, MBSE to Wire Harness Design. This is the last in a three-part series. If I'm looking at the numbers here, I can tell you there's a lot of interest in this topic, and it's great to see you here. Before we meet our presenter, there are just a couple housekeeping items that I want to go over. First is that we encourage you to ask questions. Just submit your questions in the question window, and we will address them either during the presentation or during the Q&A at the end. Secondly, during the presentation, we will have 3 poll questions, and we'll share those results with you so you can see how others respond. Watch for a pop-up window when it's time for the polls, and we'll tell you when it's time. This is the third webinar in the Digital Engineering Basics series. We're using a video drone design to make it as close to a real-world example as possible. In part 1, we covered product model development using a video drone. And then in part 2, we analyzed and performed a trade study based on business value on the video drone that we created in part 1. So today's part 3 that brings it all together. We'll take the results of the trade study and begin the implementation of the wire harness inside the drone. And with us today to take you through all of this is our exceptional subject matter expert, who many of you know already, Sanu Warrior. So welcome, Sanu, and thank you for being here with us today. Why don't we go ahead and get started, and I'll hand this over to you.
Thank you, Amy, and thank you everyone for joining. As Amy mentioned, my name is Sanu Warrior, and I'm excited to talk about the process to take a model from MBSE to detailed wire harness design. For the agenda today, we will discuss the maintaining the model relevancy, so digital engineering model and keeping that model relevant through the product development process. We will then outline the main model preparation guidelines and also discuss the process and tools for connecting the MBSE model with detailed design. The demonstration will walk through transitioning the system model into detailed harness design, and then we'll open up the floor for questions. And as Amy mentioned earlier, to keep it interactive, we'll have poll questions. So let's begin with our first poll question. And over to you, Amy.
Okay, thank you. Have a look on your screen, or if you don't see the poll, look for a pop-up window that may have come up behind. The question is, the first one is, what is your role? So just select one of the following: systems engineer, product architect, or perhaps you're a CIO, engineering manager. Maybe you're an electrical engineer, or wire harness engineer, or a mechanical engineer. If you don't fit into one of those categories, just select other, and then in the chat window, tell us what that is, so we have a good sense of who's joining us today. Oh, goodness, just about everyone's voted by now, so that's great. And give it just a couple more seconds, and then I'll show you the results. Thank you so much for your participation. All right, I'm going to close this out, and we'll have a look here. Sanu, do you have any guesses?
Oh, I'd say I'd not be surprised to find electrical engineers there, or wire harness engineers. Oh, that's a pretty good mix, though.
Yeah, it's a good mix. Very good.
Since this is about MBSE and systems engineering, I would expect the system engineers to be there.
Yeah.
And that's a good mix. What did we get some of the others over there?
We did. It looks like we've got a professor with us. And let me see if anyone else put in their response. Nope, that's the only response we got in the other category.
Perfect. And it's always great to see the results and great participation again, I believe. So let's talk about what we are, what we have been discussing for a few weeks. As mentioned earlier, this is the third webinar in the series, and I'd be remiss if I didn't recap the previous webinars to make sure we tie this all together. Or, maybe I should say something, it would be cooler to say something like previously on digital engineering basics or something like that. The first webinar, in the first webinar, the great Steve Cash from Vitech presented an overview of the system engineering process. And that included the requirement refinement, use case development, behavior development. He also got into the physical architecture, not too much detail, but we explored the physical hierarchy of the drone model in Vitech GENESYS. And Steve also explored many other areas such that the setup for systems can be done for model analysis and trade studies in the following webinars, and then of course hand off to detailed design. This picture, for that matter, encapsulates the system model status. And we had the system context in the first webinar. We had some external actors for the system established. And we had the system of interest, which is the drone, which was subdivided into remote control, the drone design, and the phone application. We then further broke it down into series of subcomponents and even sub-subcomponents to give more fidelity to the entire system. And the system was ready, and the model was ready for the next steps in the product development process. And in the second webinar, Steve further refined the system by defining some parameters for systems, subsystems, and components. He also created some constraints definitions describing the relationship between the parameters and some requirement establishment as well, such as a business value, which was a trade-off between cost, mass, operational time, and video resolution. The system model was then transferred to Alex Luke from Phoenix Integration, to create trade studies and analyze the constraints using model center application. Alex went on to explain how to use the model center to bridge the gap between the system model and the multidisciplinary analysis that is required to wrap this whole process together. Alex then performed a trade study to expose the trade-offs between the cost, mass, operational time, and video resolution of the drone system, and established the business value that Steve had set up in the earlier part of the design. From then, we were looking at creating the shortest path to establish the optimal result. And the visualizations tools helped quickly analyze the complex data to derive the optimal solution. There was a lot of data, and the 3D optimization and visualization that Alex showed was really helpful in figuring out what the optimal design and where the market needs are meeting. And that at that point, we were ready for the setup for today's webinar, which is talking about the middle stages of product development. So in the adoption of digital engineering, we've brought forth a few changes from an old design, build, text, and fix product development model to the latest model, analyze, build, and verify process. Now, we can further decompose this process into three categories. The first category is the architecture-driven engineering process, which starts with the product definition and establishing the system context, establishing trade studies, and using the use cases, behaviors, requirements, and parameters to confirm the assumptions that the early product design takes into account while designing, of course. And what we get out of that is a rigorous product definition. The next category is the model-based engineering process. And here we streamline the implementation of the product definition connect to the architecture, or connect the architecture to the detailed design portion, and establish a clear design envelope. Now, there could be many aspects of the design, and it is important to establish that design process and the design envelope to eliminate error-prone documentation processes that are used if you don't have a digitally connected model. And the final category is the verification and validation process, which is performed at key points in the design cycle, preset points in most cases, to improve the product compliance and product definition, and comply and make sure that there is no divergence. The goal is to detect and minimize the divergence between architecture and the build stages. The core topic for today is centered around the model-based engineering process, and we'll explore verification and validation in future discussions. So what does that mean? Now, I'm sure you are all familiar with the VModel for product development. We have the system, we start with that, and then we decompose that into subsystem design, and we work over here for a little bit in trying to figure out the architecture, the requirements, establishing the parameters, and so on and so forth. And then the subsystem moves into the detailed design or the implementation phase, where we're talking about detailed design on one side of the V, and then getting into the manufacturing phase and going up to testing and validation process. Now, working with the VModel with partners, it was clear that too often the model-based design process breaks down and the model gets disconnected from the product development path, right where we see the transition from the system and subsystem design to implementation. And why is that? We found that the typical process reverts back to a manual translation of the system model using documents. And as a result, most of the ROI that is performing in the model-based process is sort of lost in the product development process, because both processes start diverging from the model definition. Now, how do we bridge that gap? And that's what we're going to talk about today, is the first step. Let's look at the drone architecture here to understand that there are many systems and subsystems established and interconnected. So if we have motors in the drone, and we saw this in the first and the second webinars, there's a flight controller, there's battery, and sensor arrays and cameras, and all of these are interconnected. To successfully implement this architecture, the detailed design team must clearly understand the model. To successfully implement the architecture, they need to understand what is connected and how it is connected. And for that, a really important part is that the model needs to be ready to capture the required information and enable a smooth transition from this stage to the detailed design stage. However, a standard MBSE SysML schema does not effectively capture the necessary details. At least that's what we found. To overcome this challenge, we set up a few strategic schema extensions to capture the essential information. The type of connections between the components we realized is important to capture and communicate to the design team. For example, we might have an electrical connection between the flight controller and the sensors to give some power, or maybe it's a main power that is going from the battery to the power electronics board. We need to know that, is that connection electric from the MBSE model, or is that a data link, or is that a mechanical connection, or is it a human interaction? We need to specify that for the downstream processes to understand what's going on. It is also important to track signals and maintain connectivity. And that's difficult if we don't know what's going on. So we used items and expanded on that to have signals transferred between different blocks. The model also must clearly identify and differentiate between systems like an ECU or a PCB or a part, or even talk about something as simple as a camera that might have a connector already and it's established the part number. How do we tell that to the systems engineer? How does the system engineer tell that to the detailed wire harness designer? We used ports for that and specified, if need be, an ability to give the person the manufacturing information or maybe even the pin assignment. And this extensibility was largely due to the ability, the great ability of GENESYS to do that very quickly. So we found that to be very easy to do, and very quickly learned the transition is simplified if we have that in the model. The second part is establishing the system context and communicating the system context from detailed design or from the systems engineering to detailed design. However, exposing the entire model, this model from the system context that we established to detailed design can be very confusing and detrimental to the process. So what do? We believed that it was a good process to understand the perspective of the detailed designer and understand what's the subsystem and what's the context of our design, and understand that and communicate that. And that's where what we talked about, the design envelope, came in. So for instance, in the drone design, the electrical design team only needs to know about the drone design subsystem. And that's our context. We don't need to talk about the phone application or the remote control design at this time for the wire harness. And that brings us to the third part, or the third step, which was transitioning the model to the detailed design team. So the design envelope of the model needs to transition from systems engineering, which is in GENESYS, and pass that to detailed design. And we used our Zuken's E3 series for that. And the final transition must not only talk about the logical architecture, but it also needs to replicate the hierarchy and the topology of the model. Additionally, it should also expose the diagrams, the requirements, the parameters, and even verification requirements, so that enough information is available on the detailed design side without having to replicate everything that is on the systems engineering side. And for this stage, it's important to know that the detailed design and GENESYS model is connected using the E3 topology editor, because that forms the perfect transition from one architecture to the other architecture level. And we'll be using the E3 series GENESYS connector to transfer the architecture and expose the system model. We'll also discuss and talk about the IPC 2581 standard and how that file can be used to communicate the PCB pinout, so that we can have a robust wire harness in conjunction with what's established on the system side, without having to resort to manual errors that happen all the time. Before we move into our demonstration, let's do our next poll question, and then we'll talk about the demonstration. Over to you, Amy.
Okay, thanks, Sanu. That poll should be up on your screens now. And again, if you don't see it, just look for a pop-up window. And the question is, where are you on the digital engineering journey? Are you just starting? Perhaps you're researching. Maybe you're in the deployment phase or the production phase, or maybe you're just totally lost. And in that case, just put you don't know. So if you'll just take a moment, give us those responses. I see we've got a lot of people responding already. We appreciate that. Give it just another minute and then we'll close this out. All right, thanks very much. Appreciate your feedback. Let's take a look at the results. Ooh, more than half of you are in the research phase.
Yes, that is excellent. We are discussing the details, and it's a great place to be to find out all the information. So I'm not surprised. It's a great time to be in the digital engineering phase. So that's perfect. And some are in the deployment phase as well. So there's a large chunk over there as well. So thanks, Amy. Let's talk about the demonstration. in the demonstration today, we will first look at the MBSE model in GENESYS, talk about the schema extensions and the artifacts and ports and objects that are used. We will talk about then transferring the model to E3 series, create a functional link to the system topology using the E3 GENESYS connector. We'll also talk about how we access the model, the parameters and the requirements from detailed design into GENESYS. We'll talk about the feedback that is required, as well as talk about how to create the wire harness design and use the IPC 2581 to finally drive the manufacturing drawings from detailed design. So let's get right into it. So first, we will take a look at our GENESYS model. And let's come to that. Let's bring that in. And this is a GENESYS model that was established by Steve and in the earlier process by Alex. And we see that there is the model that's established, the system context is there, and we are in the drone design section of it. And you'll see that there is a connector here. Now, this is a connector that is already part of the camera gimbal, and we knew that this was already there. We know what the pin assignment is, what the part number is, so we were able to do that. And this is what we talked about, the schema extensibility, and also define that what type of connection it is, and that's electrical. We also realized that we don't want to get into too much detail, so we didn't establish like wires or pins, only the pins on just one connector. But in most cases, we don't know what that connector would look like in the systems engineering side. So we made this connection, which is the connection is coming from an electrical signal, and we are transferring those items that are established on both sides through that link that is established. So we did that in the GENESYS model. There is, of course, parameters established in some cases. Our landing sensor array doesn't have any, but for example, the main battery might have some parameters established that says what the battery capacity is, what the cost might be, and what the threshold is, but we don't have observed values for it from the system side of it. We'll talk about how we can communicate that back from detailed design, and we'll take a look at that from the E3 series side. Once we have established the system context, then we get into the E3 series side of it, which is the second portion. We talk about inside E3 series, and most of you must be familiar with E3 series, Zuken's electrical design suite. But if you're not, we have lots of information on our website, or reach out if you need to understand more detail. But what we have here is a topology page inside E3 series, which is a one-to-one scale drawing area, which is essentially the architecture level. And what we have here is our GENESYS connector, which I would launch, and let's connect to that. It pops up in my other screen, and we log in to the server location that might be hosting my GENESYS application. And what this is doing is going and capturing that information so I can, as an electrical engineer, see all the projects that are available to me to take a look at. And we are going to take a look at the drone design. We're working on that today. And we're only concerned about what is exposed to us, the system model that's exposing the context. In this case, I'm looking at the drone design. And there are some options that we can select to understand what we want to import. And we will just go ahead and load that into our project. When we click load, what we're trying to do is digitally bridge the gap between GENESYS and E3 series and bring that information across to the topology. And what you'll notice in the background, and let's move that to the other page for a second, that all the systems and subsystems and components have come in. They have the signal information or the ratsness between these blocks telling us that there is information flowing between all these areas. And because we're in detailed design, of course, we can start creating that link. So let me start making a few links here. But before that, let's, we can always move these about. And it helps that it is the topology is one-to-one scale. So you can establish some links as well. Let's make a link between the power electronics board, and maybe the power electronics board connects to the motor over there. And very quickly, we can establish the links. And these links are, of course, very intelligent. As you can see that we are opening up the process where these links are becoming channels for communication between the flight controller board, for example, and the sensors or other systems and subsystems. And you will see, you'll also notice that we are removing the rat's nest because it has a path now for it to be traveling along that path. And of course, we can do a better job at drawing these, but we quickly establish a drawing for it. And what do we have left here? A couple of more connections, and we will have a detailed design established. We have done all the connections, and this is where some of the interactions between GENESYS and E3 series or the MBSE and the detailed design comes into account. How did I make that? Because of course I knew how to make this, but if you didn't know or the designer didn't know, they could go take a look at the diagram and check the diagram not having the GENESYS application on their computer. We can take a look at the flow internal block and see what the diagram looks like and make that connection. Very easy for an electrical wire harness designer to take a look at that and say, okay, that's the established link. What do I need to take over from there? And the visual information really does help in making that connection. Furthermore, if as we are designing it, we can also take a look at the parameters and confirm that what the parameters are for our design, what the objectives are, and then communicate the observed values whenever we need to using the feedback option. We don't want to overwrite data inside of GENESYS, so we are going to only write specific areas that is the observed value in the parameters. We can also take a look at the requirements. It's important to know that if there is a requirement on this battery or any connection and what that might be. So for example, the battery requirements are that it's a 12-volt DC application and the battery must be replaceable. Now, the replaceable part is not essential for us on the electrical side, but it might be good to know that we should keep wires and other components out of the way of the battery and maybe give it some slack because there will be some movement if it's replaceable. And that sort of moves us into the next stage, which is to understand while we are designing, can we still communicate and keep that model relevant? So for example, we looked at the drone design from before, and let's close that and maybe make that a little bigger so we can take a closer look. If we wanted to see from the detailed design side, if you have this running on the same computer, even traceability is there, and that communication is important. If I want to highlight that signal and see how that signal or how that connection is established and implemented in detailed design, I'm able to make that connection between the GENESYS and E3 solution. That highlight tells us that that is a connection. Or if I wanted to make sure that I understand how this connection is established, I can take a look at that and highlight that, and we'll see that that link is clear as well. So there is two-way communication happening to understand and use the context clearly. Now, how do you take that information and get that into a schematic or detailed design? So let's take a look at the schematic. What we have here are a few components. So we said we have a J1 connector, which is on our camera gimbal, and we can drag and drop that to just make sure that we know, okay, there's a camera gimbal over there, and we can place that in the schematic. But before we do that, we do have a flight control board. And we talked about IPC 2581 and how do we use that, because the flight control board is coming from a different team. That is, we will use our IPC 2581 file to take the export from our board design team, select all that information, and let's place it on the selected block. We'll have the existing name and add it to the drawing. Now what we're doing is we're taking the information from the board design, which is the IPC 2581, of course, as you might know, is a standard export for board designs, and bring that in without having to rewrite it or edit it or format it, and bring that into our detailed design. And we'll see that there are 5 connectors that we brought in, or 6 rather, 6 connectors, and even the signals on that. So let's place that onto our board here, and you'll see that the connections are being established. So very clearly and easily, we can start putting our board together in the E3 series. Let's place that, and maybe some of this. Now, what's the benefit of this? Right? It's a common question. How does this help? This helps because our model is a single source of truth. So when we brought in the model, it was not just some topology blocks and systems that it brought in. It brought in entire components. Now, we didn't have an established part number for the connectors, but it knew what the signal was. So we brought in the signal information for in our system model, and said maybe those are connectors, and we can use that. So for example, let's take a look at the front sensor array. We can see there are a few signals here, and there are 4 pins because there are 4 signals. And in E3 series, what we're able to do is establish, okay, let's take a part number and say that's the part number because in a detailed design, I'm using that. And as a detailed designer, I'm giving it a name. So that's my connection and part number. The other one might be, let's say, take a landing sensor and take that connector, and I will give that, maybe that's an 8-pin connector for me, and let's give it J12. And let's take the rear sensor as well. And let's make that an 8-pin connector. And let's call that J13. Okay. So as a detail designer, I started creating some components. And I can see them here, of course, the J11, J12, and J13. And now let's see what happens when I place this information on our schematic. So there is already some connections happening. Now, remember, this board was brought in from the board design team, and this information was brought in from the systems engineering side of it. And in the detailed design end, we can very easily establish that connectivity and make sure that we are establishing the perfect communication options here. And of course, we can at that stage start making the connections and establishing the links as required. And we will also see that we are able to only connect the parts that are linked. So for example, the video 1 connects to video 1, and that's our obstacle video. If you try to make a connection between 2 opposing signals, it'll stop that. So that's E3 series and the online DRCs that are making that happen. Very quickly and easily, we can start establishing our detailed design from the information that we brought in from MBSE and using the IPC 2581 import to establish the board. Now, for the interest of time, let's not make too many connections here. What I'll do is I'll close this project and we'll move forward. But before I do that, also notice that we have some the harnesses that have been formed sort of because we made these connections over in the topology. So E3 series is starting to put together, okay, all these items might be from a single harness, or that might be a single harness. And this connection, all established, might be harnesses. And we can then look at how we can combine these to make sure that we can complete a harness design. So let's close this, and do some magic and move forward. So let's open the project, and we still have our topology. It has a little more detail now, and we have our schematic that is established. Basically, we connected up all the cross connections and placed them accordingly, and added some wires as well to match that information. Now, how do we add wires? And this is, of course, the beauty of E3 series, and the information is pretty clear. If we add the right size of wire, we can add that over on the connections itself. And if we didn't have the right size, so for example, if I tried to add a 10 gauge wire, then it might say, okay, it might add, it might not add. So it is basically establishing a connection on the properties of the wire and the connector. And that all is, again, coming from the intelligent library that we're using. So let's take a look at the harness that we are establishing here, and that will be made up of our flight control board connectors and the connector for the sensor array. To be precise, we'll be looking at the flight harness, and that will be our connection right over there. And in our form board application, we are able to go and place on form board, and that will give us this neat little trick where we will be able to get every connector, every point of connection that needs to be made, and we can go and place that inside the form board, which is the 1-to-1 scale harness manufacturing drawing, and make sure that those connections are made. Let's place that over there. And we'll take a look at how we can quickly analyze this information and put that together for our manufacturing team to establish the harness. Now, of course, this is a fast forwarded view of what might happen. And let's see, maybe this way. And of course, you can pick and choose which view you want to. I'm putting most of the side views over there. And we have a connection that we can make. And very simply establish the links and paths that are required for this harness to come together. And you'll notice a few little details that you might have already noticed, but let me point that out. These are red dotted lines because it doesn't have a true length, and we can put that in. We also know that there are conductors flowing through them. These tables have established what the wires are and the colors that the wires have. Some of them are white, some of them are black and green. And all this information is possible because of our harness builder application. Now, there's a lot of neat little tricks you can do to make sure that the design is moving quickly. For example, we can create a bill of materials on the page. So we can place the bill of materials, and all the established bill of material information is going to be there. It'll even produce an Excel sheet if need be. So all this information that you might already know, and if you don't, again, we can talk about that in more detail in a separate conversation. We can create some wire tables to make sure that we have the information for cut lengths and descriptions for that. And all of a sudden, we are getting ready to establish our design and start communicating manufacturing. So that is the information that we put together. So at the end of the day, let me close this and show you the complete design, and then we will look at the summary of this. Okay. So our form board, if we were to work on that a little bit more, would look like that, with some lengths established, and automatically add some tape and coverings, and basically create this such that it can be shared with manufacturing. And of course, there are more details. The key here is we started off with just a simple design in GENESYS, brought this in, and communicated the parameters and looked at the information in GENESYS and being able to put that across. So for example, we have our topology here, and being able to say from the battery, go and put the observed value of battery capacity or cost or mass, and then being able to take that information and communicate that across is crucial. And we, of course, did that using the GENESYS connector. That brings us back to the poll question that is next, which is over to you, Amy.
Okay, thank you, Sanu. This is our last and final poll. So again, look for that pop-up window if you don't see it right away. The question is, how do you transition from systems engineering to detailed design? And just go ahead and select one of the following. You're using documents and manual processes. You are actively looking for the answer to that question. Your MBSE system does not drive detailed design, or perhaps you have an automated process that's already working for you, or you don't know. None of the above. Take just a moment, tick one of those boxes for us. Also, if you've already taken the time to answer that question, I see we have quite a few questions coming in for us. Please continue to put your questions into the question dialog box, and we'll get to as many of those as we can here in the Q&A section in just a moment. All right, we'll give it just another minute before we close this out. Okay, I think we'll close it out now and we'll have a look at those answers. There we go.
I'm surprised there are a few, none of the above. And we do always put the option because there are none of the above, but 10% seems like, but the rest of it sort of makes sense. It is a manual documented, document-driven process these days. And hopefully throughout this process that we discussed from the first webinar to today, we've been able to establish that there is a digital process that we can follow, and we can discuss that further. And whoever has more questions, of course, we can jump right into the next portion, and then we'll get into the questions. So what are our webinar takeaways for today? So top 3 things I'd like to leave you with before we get into the questions is what we found is extending the model schema helps capture the information to guide detailed design. The extensibility of Vitech GENESYS modeling schema was essential for us to capture the ECU information, the signal information. It also was pivotal in us making sure that we can handle reuse blocks and pre-configured parts, such as the gimbal, which had a fixed connector, and for easily managing those signals between different subsystems and components. The second part is the MBSE model is not a schematic. And I know that seems very simple, but it is not. It's we've seen a lot of ways that people have been trying to make it a schematic, and we also thought about that, but we understand it's important not to fall into that trap of capturing too much information in the system's design tool, because that's not the place for it, and that information is not available early on in the process. The MBSE model should link to the detailed design at the topology architecture level or the system interconnect level, and be able to glean information and use that information to do more of a translation rather than being a rework of the same information. And the third and the final point is that the system model is the source of the truth, and therefore an on-demand reference option between the detailed design to view the MBSE model is imperative to the success of the electrical engineer, the wire harness engineer, and even the mechanical engineer for that matter. And a feedback loop to update the model parameters or just communicate the information accelerated the model refinement process for us. It's not just that improved the detailed design portion, but it also helped communicate the information to system engineers so that they can refine the system seamlessly and provide us the feedback and push that across again to detailed design to make those changes. And it also helps, most importantly, to keep the model relevant throughout the product development lifecycle. And on that note, we can jump into our questions for today.
Okay, great. We've got quite a few. No, go ahead.
I'm, open to it. I'll start taking a look at it. Anything jump out at you?
Yes, as a matter of fact, we have quite a few, and I just want to remind everyone to continue to put your questions in. We'll answer as many as we can, and if we don't get to yours specifically, we will certainly follow up with you after the webinar. The first one we have is from Darren, and he's asking, what is the source of information during the design process? Is it E3 series or is it GENESYS?
The source is GENESYS. It is, the information was received and will be received from GENESYS as the, but of course the E3 series portion of it is also taken into account. So for example, a simple example might be the connector. The connector information was coming from GENESYS, but that connector was also there in the E3 series library. So we were readily able to use the information from GENESYS to relay that information and reuse that information inside E3 series. I hope that answers that question.
Okay, great. Moving on, we have a question from Tracy, and she's saying, can I define harness wires in the MBSE model?
That is an interesting question. Can you define is, of course, yes. You can define. I would say you shouldn't define. The wires on the MBSE side will make things very complicated, just makes the design very, well, not nimble, let's say, on the systems engineering side. And some of those decisions have to happen on the electrical side. A better solution we found is to establish signals. And one signal could be going across multiple systems and components, and establish those connections as and when required inside the detailed design. We can also establish connections basically based on the pin. So for example, you might say that I have at least 5 connections between 2 components on the MBSE side, because you know that from a previous design, or you know that from other areas. But we suggest not to use wires. I think that's too much detail.
Okay, thank you. We have a question from Guy, and he is asking, how are wire lengths imported from MCAD tools like CATIA?
Well, that's an excellent question. We didn't talk about that today, but there is an entire process in E3 series that you can take into account for importing the wire lengths from any MCAD system like CATIA. We have something called a 3D routing bridge that might help, depending on what your CATIA model looks like, if you're routing wires or just routing splines and then attributing that these wires might be flowing through the splines. We have different processes that we can discuss further if you want that information. But basically, it's from the form board that we establish right at the end of that demonstration that we can establish the wire lengths.
Okay.
Hopefully that answers that question.
We have one from Kevin. Kevin is asking, does E3 support multiple schematic diagrams?
Yes. I assume, well, I'm saying yes, but I'm not sure what you mean by multiple schematic diagrams, Kevin. E3 allows you to have many views of the same information. So for example, the schematic diagram could be represented many ways inside E3 series without the information being duplicated. And even the form board was just another view of the schematic information. You can have a system level information right on the topology. Everything is interconnected. It's the same model.
All right. We have one from Luke.
I see. I think Kevin responded saying with a follow-up on that.
He did.
For large scale projects, it will cover many drawings. Absolutely. You can have as many drawings as you want. depending on how many drawings you need. You can even break up a schematic into multiple pages and so on and so forth. Even those blocks, that PCB itself could be broken up intelligently into many sheets of drawings. So you're covered there for sure.
Great, thank you. And thank you, Kevin, for clarifying that. We have a question from Luke asking, how can you manage architecture update into the detailed design? Is lifecycle control possible?
That's an excellent question, Luke. We are battling with that question day in and day out. We have some great ideas and we are focusing on different ways. The not so simple answer to that is the life cycle itself varies so widely across companies that we'll have to discuss what your life cycle is, what you want established as a single source of truth. Although we say, the GENESYS model should be, and there should be a digital thread connecting all of that. So we can control that, but we're actively trying to understand different ways to do that. So we haven't found a common ground that applies to everybody. So we should discuss that further in a separate conversation to understand what your requirements might be and take that information to put together a way to control information throughout the life cycle. But the short answer is yes, it is possible. We have some working theories and examples, and we're working towards tools to wrap that in a nice bow, so to speak.
Great. We've got several questions, but I think we're going to have time for maybe two more before we wrap up. One is from Larry, and he's asking, do you need GENESYS and E3 series on the same machine?
No, you do not. I had it on the same machine just for our demonstration today, but GENESYS can be on a separate server somewhere, and E3 series can be on a different computer somewhere, and you'll be able to establish that connection as long as, of course, you have the network access and the permissions and so on and so forth. But you are able to. Now, let me rephrase that just a little bit. A caveat is that if you wanted to see the GENESYS on one window of your computer and the other window should be E3 series and communicate like cross highlight, you probably want the GENESYS application running on your computer, but the server and the information doesn't need to be on your computer. Okay. Hopefully that answers your question there.
Great. And we'll take the last one from Roberto. How do you import from the IPC 2581 file for the PCB?
That is an excellent question. And I say that because I'm not entirely sure how to give that into it's a pretty detailed answer, but the simple answer is we have a tool which imports the IPC 2581 information. It parses through the IPC 2581 standard file and extracts intelligently extracts the connector information and the connectivity information and the signal information to be able to put that into E3 series. But if you don't have that tool, there are other ways to sort of look at that, but we can discuss that further if need be. Hopefully that answers your question.
All right. Thank you so much, Sanu, for that. I see we have a very long list of additional questions. And if we did not get to your questions today, we will follow up via email. Rest assured, we will answer that question for you. So with that, we will conclude today's webinar. Thank you again, Sanu, for all that information you shared with us and for handling the questions, since there were so many of them. I would encourage all of you to connect with me and to connect with Sanu on LinkedIn so that we can continue this conversation. And please also follow Zuken on social media. An on-demand version of this webinar will be available in, I'd say, about 24 to 48 hours. If you want to view it again or share it with a colleague, just watch for an email or visit zuken.com in our webinar library and you will be able to find it there. Again, 24 to 48 hours. This event is part of our 2021 technical webinar series, And like I mentioned, you can visit our library of technical webinars on Zuken.com for more informational topics, including parts 1 and part 2 in this series. As you leave, just take a moment and answer our survey to let us know how we did. It's just a single question, and we really appreciate your feedback. So thank you again for attending, and have a great day.